Got it. Okay. Yes. So, as let's say our aim is somehow to deal with the real world data, then this data is very often hidden in a form of a time series that is sampled over some usually large dimensional complicated system that we don't know, and what we have usually are some, let's say, low dimensional measurements. Yes, so such measurements are called observable. And so it's been of interest, yes, for at least a couple of last decades, how to deduce some information about original high-dimensional system from these measurements. Yes, often measurements just of a single quantity, and it is possible, let's say, through the time delay embeddings, provided that a couple of conditions are met, and these conditions are captured, for example, by Tarkel's embedding theorem. But this is some very, let's say, simple example that we usually start this talk with, especially when we talk to people who have more, let's say, experimental than mathematical background. So this is the well-known Lorentz system. Yes, so it is continuous three-dimensional dynamical system, and we choose values of parameters where it is known that it produces this famous butterfly-like attractor. Yes, and we consider some time series produced by some time t-tau step maps. Yes, so we, like, let's say, we sample these trajectories of continuous systems, and this is on the left the original original time series generated from the Lorentz system. In the center, we just see a three-dimensional embedding of the x coordinate, yes, of the same time series. So in other words, we look into these points, yes, but each of these points consists of three coordinates, yes, x, y, z. But now we look only at x coordinates, and we have points like, for example, x1, x2, x3, yes, the next point is x2, x3, x4, for example, and so on. So we produce this three-dimensional embedding of just the x coordinate. And as you see, the picture is, let's say, similar, yes. Of course, this is it's only a picture, yes, and originally, I think that the Lorentz attractor has a box dimension greater than 2. So according to classical Tarkel's embedding, this embedding dimension that allows you to reconstruct it should be, I think, 5. Here we have 3, but I think that some other versions, like probabilistic Tarkel's embedding theorem, can explain that yes, with actually good probability you can recover it just in 3 dimensions. However, for example, yes, if you only look at the z coordinate, then you do not like reconstruct it. You don't obtain the equivalent system. The system is sort of semi-conjugated. Yes? To the original one. So yes, so z coordinate is not this, let's say, generic observable, yes, but that's what x and y are. Okay, but what was actually the most important for us was the fact that Tarkel's embedding theorem establishes actually topological conjugacy between the original system that we don't know and the system that is reconstructed, so that lives in d dimensional embedding. Yes, so in D-dimensional Euclidean space, yes, provided that D is large enough. And the conjugacy, yes, is given by is actually the embedding map. So this means that if we have, for example, two time series, and apparently they may look totally different, let's say, but if they come, for example, from the same system, that is an equivalent state, and if we make their time delay embeddings, and if in both cases, if we choose, let's say, good embedding dimension, then although they may come to different measurements, they actually give us the same information. They reconstruct the same system, so they both should be conjugated to each other because they are both conjugated to some original system, yes? So our idea was to look at some methods of, for example, estimating the embedding dimension and checking if they can be applied to sort of testing the notion of conjugacy or semi-conjugacy of time series. I mean, so conjugacy is defined maybe not for time series, but for like systems or trajectories. So in our case, either we consider trajectories of dynamical systems, or if we have a time series, then we choose, we firstly do their embeddings, and we consider the embedded trajectories, and then we are always in a sort of discrete dynamical system setting. Okay, so one of such, let's say, heuristic methods of estimating embedding dimension, because in real nobody knows what is the if you don't know the system, then okay, you don't know the both dimension, the house dot dimension, the vector, and so on. Is the method called false nearest neighbor, so FNN for short, abbreviated, and it was developed by Kenneth Brown and in 1992. What's the idea of this method? So let's say you perform d-dimensional embedding from your time series, and you look for so-called false nearest neighbors. And I will explain what the false nearest neighbor in a moment. And if the number of, then you increase your dimension by 1, and you again compute some statistic that is called the number of false nearest neighbors. And if it drops significantly, it means that your previous embedding dimension was not enough. So you need to consider at least, let's say, d+1, then you check it for d+2, and so on. I will have perhaps some illustration. So it is based on some intuition that we assume that our time series comes from deterministic system. So, for example, if we have, okay, I know that this was complicated, but if I have a point, so this is d-dimensional point in my obtained by my d-dimensional coordinate map, yes? So I am in dimension d. I look at this point, I compute its nearest neighbor, yes? So the point that is the closest to its Euclidean distance metric, yes? So let's call this point SK, and so on, yes? And next, I like add one dimension, so I look to like one step forward in the future. Yes, so I take this point and I add this one more coordinate. Here I have a black L, yes, but it can be 1, does not matter. And I do the same with this point. then I check their distance. So I know that these points, when I only look at their d coordinates, they were close to each other. But then I check if this distance, if it increases significantly, if I look for their, let's say, nearest evolution, yes, in the future. So if by adding this one next coordinate, if this distance increases by some factor r, so r is a parameter of a method, then we say that these points originally, they couldn't be, let's say, real neighbors, they were so-called false nearest neighbors, because if they were really close to each other, then their future evolutions cannot differ too much. Of course, what is too much, then nobody knows, but this is expressed by this parameter r here. So you need to, of course, check many of these parameters. And the intuition comes from the continuity of the systems. Yes, so for example, if I have I have two points in 5-dimensional space, then it may happen that if I only look at the first 4 coordinates, they are the same almost. But if I look at the 5th coordinate, I see that they are different. Okay, so if something like that happens.
Excuse me, what is capital M?
Oh, it's the length of time. I mean, it's the number of points like that. So it's if you have a time series of.
The total length of the time series?
Yes, I mean the length of, because if we have a time series, yes, and then from this time series we perform
more or less, it is.
It is, yeah. It's just like
time series.
Yes, yes. It's how many DI vectors you can produce out of n dimensional time series by sliding window embedding. Yes.
It's level time series minus the.
Yes, because.
So it's minus, so it's not divided by the time?
No, you need to fit.
Okay, so it's shift. Okay, you know my knowledge. Okay.
Okay, so if we notice, yes, that this distance increased by r, then this contribute like 1 to this sum here, yes, and we do it for every point, yes, for every d-dimensional point. So here this term, it just says that if originally our points were more than this factor apart, when sigma is the standard deviation of the data, then we just don't count such pairs as false nearest neighbors, yes, because it means that, for example, this point was a sort of like outlier in our data set, and that does not make sense. You need to look for a nearest neighbor. So here is the normalization by the number of these, let's say, outliers. And finally, we obtain some number, yes, that depends on R, and of course on our D, that we chose here. So this is so for different values of D, like D1, D2, and so on, yes, and different values of R, we compute such curves that are just the values of the statistics. And if it drops significantly, yes, to 0 with some R, then we can use that, for example, this and this embedding dimensions are probably enough. Yes, so it's a sort of heuristic, but actually I remember some time ago I talked about this false nearest neighbor method with Anna Śpiewak, and he had a feeling that actually explanation of this method, why it works, let's say, because it does not have a proof in the literature. Yes, it's a sort of heuristic that sounds reasonable, that maybe it can be explained by results of Dynamical Buchman and Śpiewak on this probability predictability conjecture. We had a feeling that it's connected.
We're confused by this graph, because I guess what we want to fix some R and then understand when this normalized number drops, right? And here it seems that you are doing it as a factor of the R, right? So
yes, I mean,
But different graphs correspond to different D, right?
yes, different
okay,
curves.
so it's like this is the
This
I
is
don't
like
know.
D1,
Okay.
for example.
This is what I
D2.
was missing. Okay.
So, yes, because this factor you don't know, like you don't know what to choose. It may be something connected like with the I don't know, some Lipschitz constant of the function. Yes, and okay, so so our first idea was actually okay. Look at this in a bit more general way. So imagine that so equivalently, yes, instead of this embedded time series, we can think about actually some trajectories, yes, that we assume that they come from some deterministic systems, though we don't know f and g, yes, this function. So, so f is a mapping from capital X to capital X, yes, g is a mapping from Y to Y space, and we sampled two trajectories. They're finite, yes. And here we can just so the distance it can be replaced in general by the metric in these spaces, yes. So we only need them, I think, to be Hausdorff spaces. And here we choose a point, let's say AI, in our first trajectory. Yes, we look for its nearest neighbor in the same trajectory. Yes, so that the other point which is the closest to it. And then, in the simplest case, you can just consider the bijection. Yes, by matching the same indexes in one trajectory and the other. Yes, so my point AA in the nominator corresponds to point BI in the numerator, and I also need to map like find the corresponding point on this other trajectory, yes. And this gives you sort of I don't want to say maybe conjugacy, but a sort of, let's say, conjugacy or similarity measure between two time series if we consider, identical matching between the indexes.
Sorry, I'm confused about this function. So kappa is a collection of k points, right?
Kappa, yes, you mean here, yes, the set of k nearest neighbors, yes. But here I think we only have in this formula we consider the first nearest neighbor, yes?
So you just take one.
Yes, because, I mean, of course, it's possible, to generalize, but here we just have a distance between the 2 points. So I choose the distance between A and its nearest neighbors in the same term.
So the formula, this complicated formula, we have dy of bi, and psi of this expression is just whatever bj we obtain in
yes.
bijection. I see.
Yes, if for example here you have AI and AJ is this nearest neighbors, then here I have BI and BJ. Okay, so but perhaps it's also possible to consider some more complicated matching here. Okay, so I'm mentioning this because so let's say this is one method, one possible test of conjugacy between time series or trajectories. The other is somehow simple, but also somehow more complicated. I mean, we decided indeed not to look only at the first nearest neighbor, but to look at, let's say, k nearest neighbors of a given point, and k is again some parameter. So this is some picture, yes, so imagine it's a simple picture, yes, that we have some trajectory, A, and here we have the other trajectory, and we somehow look about the, let's say, discrete approximation of neighborhoods of points, on corresponding points on these two trajectories. So, for example, if I choose point A6 and I choose k equals 4, I look for 4 nearest neighbors in A of this point A6. Yes, so we have A3, A4, A8, and A9. So if we want to check, how they are similar by exact matching of indexes, that means that here I consider point B6, yes, before B3, and here I have B8, B9, yes, but it's really that, like, geometrically this and these neighborhoods are different, because here I have two other points, B5 and B7, which are closer to B6, yes, then, so actually, if I want to include correspondence of all the points that were here in this neighborhood, then here I need to consider not 4, but 6 neighborhoods over corresponding points, so over point B6, yes? So, this is a sort of like measure of the difference, yes? 6 minus 4 equals 2. It's a sort of measure of the difference between discrete measure of these two neighborhoods. And we do it for every point. We add it and, let's say, divide it, and in this way we obtain a sort of like similarity of A versus B. Yes, so this is this formula says what I just told about. And as you may notice, this measure is in general not symmetrical. I mean, calculating it like for B versus A may give you a different number. And heuristically, because this is like not true, but let's say conjugacy is reflected by both these values of TNN AB and TNN BA small, and having relatively small value of one of them indicates a semi-conjugacy. Yes, I mean indicates if the systems are semi-conjugated, then you should obtain a small value of that. So these methods are, let's say, quite heuristic, but we have also developed the other two methods which are similar to each other, and for them we have also some proof. So maybe let me explain them, because the formulas are I know that they are always not so, maybe not so nice, but in fact what they say, it's not so complicated. So our first method, we call it like conjugacy test, so of time series A versus time series B, when K is again a parameter, so this is actually this K nearest neighbors. P is some time step, because maybe we won't just have t equals 1, or maybe we want to project our points like t time step in the future, and then convert them. And H is some sort of candidate for the topological conjugacy. And this is, of course, the problem that usually you may have no idea how this conjugacy should look like, but Michał will later comment a bit on that. I think I will go to the picture, because to explain what's here, I will go to the picture. So we need to, in particular, know what is H tilt and H tilt plus. Yes? So this is some picture when k equals 2. So we have some point, let's say AI, and we look for its two nearest neighbors. So these are these 2 points. if we have some idea or if somebody gives us a candidate for this function h, then what we do? We compute h of ai. Of course, as it usually happens, exactly such point may not exist in this second time series, so in this time series b. So what we do, okay, we just look for the point which is the closest to it, yes? So we denote it by h tilde of ai. Then we do the same with these 2 points, yes? So again, we match them by h and look at their, let's say, best approximations in the time series we are provided. So in this way, we obtain like h tilde of this ua2, so of this blue set here, yes, it corresponds to this, so this is its image under the mapping h tilde.
So H tilde is a collection of 3 points in this case? Or-
Yes, we also we consider, I think, a bit technically what happens if, for example, there are 2 points in the time series that are, you know, let's say they approximate this h of a in the same way, yes? So,
I mean, the H tilde is, will have, if k is equal to 2, it will have always 3 points or less. If, for example, if for 2 points, its image is closest to the same point in the time series B. And the H tilde will be not bigger than the k plus 1 almost.
okay, so for a moment, maybe let's don't think about this that count, but what we do here, yes, let's look at this formula. So, okay, let's say I computed this set, U, A, superscript A. I can match these points t times further in the future, yes, because I have a time series or an embedded time series, so like a trajectory, yes. So I know that, for example, point, you know, a vector of points that starts at point ai, it corresponds to, in t times steps in the future, it will be the vector that starts at the point with index a plus t and so on, yes, because here there will be this order. So I compute the image of this set under f2, yeah, ft, so I have another like point cloud chosen among my a time series, and then I compute its image under function f, and I still stay, you know, in this. So this is what I have here. I have some, let's say, point, and then I look what happens if firstly I compute the image of this point cloud under h tilde. So I have this set here. And then I projected t times steps in the future in this b time series, and I obtained like another point cloud. So in a perfect situation, when h gives you a semi-conjugacy actually between these 2 time series, and if we can, if this really well approximates this time series, if it approximates in a nice way this time series that is here, then these 2 point clouds, they will like overlap, let's say, in a perfect ideal situation. So that means that the Hausdorff distance would be small. We choose a Hausdorff distance here, but I think it's also possible to consider some other metrics between sets. Yes, and we do it for every point with our time series, and we sort it back normalize. Yes, and in this way we obtained this value that we called conjugacy yes, of A versus B with these parameters.
So question, but even if H is a true conjugacy, still it's possible that because it distorts thing, the Hodor distance above will not be zero, it will be some positive number because some points
Yes.
will stretch. Okay.
Yes, because I mean it's also this problem. It's also here that here
Yeah.
it's, I may not exactly find this point, but okay. But actually, this sometimes this test it may give you, let's say, false positive answers. I mean, it produces relatively small values for systems for which we know that they cannot be, let's say, semi-conjugated, conjugate. So instead, we wanted to consider, let's say, a bit enlarged neighborhood here. So it is similar idea like with this KNN test. Yes. So for example, it happened that when we computed this blue set, then we have 2 points, but there are also another points here, these 2 points, which are closer to this point, to our, let's say, theoretical point, H of AI. So let's say it's a sort of reasonable to also include these points in this point cloud, and in this way we have like a large neighborhood which we call H tilde plus, yes, and if we substitute it here, yes, instead of this simple set, and then everything is the same apart from that, and we have like conjugacy test plus, yes, so we have, let's say, 2 tests of assessing the similarity, yes, between 2 time series given by some corresponding matching H, yes. And it's actually not hard to justify, yes, that, for example, if our space Y, so this space where time series B lives, if it is compact, and if we have always like finite time series, yes, but if it's sampled along a trajectory that is dense in Y, then if we sample it for long enough, then in actually, and if 2 systems are indeed semi-conjugate, yes, so if G is semi-conjugate to F via H, then you can show that with M going to infinity, so actually the length of this first time series here does not matter, what matters is the length of the second time series, then this will go to 0, so if systems under these assumptions, if systems are semi-conjugate, then these tests should give us long values, yes, provided that we sample long enough. And of course, the proof is based on that analysis one method, yes, the uniform continuity over compact space, and yes, and applying semi-conjugacy formula, yes. So of course, immediately we also obtain this assertion 2 here, yes. So if we know that systems are in fact conjugate, and if this first space is also compact, it also is something along a dense trajectory. So we may think, in some real setting, we may think that in fact what we sample some omega limit set of some trajectory, yes? And our spaces X and Y are in fact omega limits in these trajectories. So then, of course, we have both these values going to 0 asymptotically. So but as I mentioned, this test, it may give you actually false positive answers, so it was a bit harder to prove that to prove the convergence for this conjugacy test plus, yes. But you can also prove it that if both the spaces are compact, so both samples are taken, are long enough samples over dense trajectories, then this conjugacy test plus for semi-conjugate systems will also converge to zero. And here I
So,
would-
I have a question. So in the previous theorem, if you replace conjtest with conjtest plus, it will not hold in general. In the previous
I
theorem.
think that there was actually a problem with, you know, that these points were really, although they were close, they seem like close, here we couldn't control the.
I think it was not a problem with the theorem or the. I think we left it as a hypothesis because the theorem becomes.
No, but we prove it for conjugated, yes, I mean, conjugated test plus, yes? Yes, but we needed indeed like more assumptions, because here it's only semi-conjugacy, but I think that yes, so this is what we obtained. We had some problem with just having, let's say, this and density and compactness of this. I mean, like, so let's say if we want to justify this, then it's also not so, it's maybe a bit longer, but still the methods are not so super sophisticated. So we did it this way, that we need to estimate something like that. Yes, so we split it into two sums, yes, because this, okay, this set is contained in this, yes, and this, but this converges to zero basing on the previous theorem, and we want to deal only with this part, yes, but again, yes, but again we can have by using the fact that G is uniformly continuous on space Y, yes, H is also a mapping between, it's also a map over a compact spaces, continuous map, so we can uniformly control the distances between the points. And then from of course, the density of the second time series, yes, we know that every point in space Y, it can be, let's say, well approximated by some point that we have, yes. And similarly with the first time series A, yes, we can, I think this is because the space is compact, so we can have like a finite subcover, yes, we can control the diameters of this set, yes, so this is for every epsilon and K and T, which are fixed. Yes, and then we can estimate something of this kind. So I think I'll maybe not go through this very in detail, but yes, so I mean by this assumptions, I'm able to control the diameters of these sets and they still will approximate the points that I want to approximate. And in particular, so if I have a point, yes, that belongs to this set, let's say H2 plus, not behind here, then by the way I define this this set with plus, it cannot be far away. I mean, if some point is here, then that image of this, it cannot be far away from this point until that here. It is because actually, we define this set with plus by that these are the points that are that they cannot be further away from a point I than the points of a set H tilde. Yes, so finally I'm able to control everything just to conclude this reasoning, and we obtained a sort of estimate, yes, upper estimate that can be as small as we want. But indeed here we needed to control, let's say, more things than just in a conjugacy test version. And I think that now it's time for Michał, yes?
It's almost perfect. Okay, so I'll continue with some examples about how do we try to use this test that we develop, and this is I'll start with maybe rephrasing or using a picture to rephrase the definition of this conjugacy test. I will actually focus on this conjugacy test instead of, and I will keep the FNN and KNN. Maybe I will just mention it one or two times. I want to focus on this conjugacy test. So to rephrase, because as Justyna already mentioned, this formula is very horrible, while the idea is very simple. It's just difficult to put it in a compact way. So what we are trying to do with this conjugacy test is to somehow mimic this commutativity of this diagram. So what we are doing, what we are trying to do, capture with this formula is that, so if you imagine that we have two time series, so what we are doing, we start with some point, we take the discretized approximation of the neighborhood of this point, and we look for a counterpart of this neighborhood in the second time series, and we don't take exactly the points that we get by the mapping of the neighborhood, but we take the closest points, because we all want to make use of the dynamics that is encoded in the time series, and we push those two set of points by the dynamics forward. So by pushing those points forward means that we just take corresponding, we just shift the indices of those points according to the indexing in time series, and then we map one of the time series again. So in some sense, by picture, we simply mimic this diagram with using just a finite amount of data, and at the end we just compare how pushing this neighborhood, one way and another, how these different ways will differ. This is the intuition what we are trying to do. Okay, and we started playing with this idea with a super simple example. We took a logistic map. I assume, or I guess all of you know what it is, but again, these are slides for prepared for more general audience. So we know that a logistic map is just a simple function that is iterated over itself. So as a result, we get a time series, and the feature of logistic map that interested us is that it's very sensitive to initial conditions. So if you just take the starting point slightly perturbated, the resulting time series will be significantly different. So if I take the same dynamics but with slightly different starting points, as a result, we will get two time series that are but desynchronize very quickly, and we get two-time series. Yeah, they are completely uncorrelated, and this is an example where we would like to detect that these two things are actually comes from a similar process, right? And a simple statistical test will give us nothing because they are uncorrelated, but we would like to see beneath the data to see this dynamics hidden inside. So for this very simple example, when we take those two-time series generated by the same map starting from slightly different starting points, and we compute the tests that Justyna mentions, for conjugacy tests we get a very small number. All of these statistics will also always lies between 0 and 1. So the smaller the value, then smaller values suggest that those time series comes from more similar dynamics. And this conjugacy test for this example gives us a very small number. It would decrease the longer time series we get, because it will always be greater than 0 because of those approximations, but we'll get smaller and smaller values. FNN and KNN unfortunately are very sensitive to all perturbations, so even we compute our examples for all of them because they were our initial inspirations, but we can see in our examples that in most cases they are maybe too sensitive to deal with noise or with more chaotic behaviors. So that's why we focus on conjugacies.
This example, because you need to choose this H, right?
Oh yeah. So for this example, it's very easy because H is identity. So, but I will get to more complicated thing. But yeah.
Tested it over identity. So, like FNN and KNN, they have flagged values, so they say that systems are not complete, which is like, let's say, correct, yes, from the mathematical point because they are different, they are trajectories of the same time series, but like these points live on different orbits. Yes? So let's say if you want to have like a sort of binary answer, like you test for, let's say, pure mathematical conjugacy, then this FNN and KN, I think they give like sharp answer. So when system is not conjugate, they like, or when you choose not trajectories which are not corresponding, then their values increases. But conjugacy, it's like let's say it increases slowly, which is okay. It maybe if you want to test for pure conjugacy, then this FNN can like detect that it's not conjugated, they detect it faster, but conjugacy does it behaves sort of continuous, yes, with respect to, let's say, change of a starting point, and this is if you treat it like a sort of similarity measure between time series of some, let's say, real data or numerical data, then it might be in fact advantageous, yes, because you.
Yes, my question was because I saw that you were pretending that you don't know where it came from.
Yeah.
And then it seems that you have to search in some cell space of the H. Am I correct?
For now, I'm assuming very naively that H is just identity. Yeah, but I will get to it in a moment. Yeah. But this is definitely disadvantage of this conjugacy test that we require this H to be given, and we are aware that this is very naive, but I will get to it in a moment. For now, we are assuming that we always use this identity as an H, because for this example it makes sense, because this is just the same system. And yeah, so this was very easy. So then we started to experimenting with slightly more complicated cases. So we wanted to see what will happen if we take time series that were generated by logistic map, but with slightly, not that slightly, but with different parameter values. So we have 3 parameter values for the classical one, 3.95 and 3.9, and again those time series will desynchronize very quickly. But we can see that even though we changed the parameter, the conjugacy test values are still not so big, maybe indicating that these time series still have some kind of similarity. And this might be yeah, as Justyna mentioned, this might be. You may say that this is not actual conjugacy test then, because the conjugacy test conjugacy was the inspiration for this statistic, but we don't claim that this will exactly tell you conjugacy between the systems, because we don't know them, but we want to see just from the data if this dynamics behaves conjugacy.
It detects the degree of being similar.
Similarity of behavior of this time series.
The more we perturb the parameter, then the greater value of conjugacy test we get.
And yes, and we compare slightly different systems, but I still use here this very naive identity mark, this H equal to identity. But the interesting thing is maybe we can focus just on the solid lines which corresponds to conjugacy test. So what do we have here? We have conjugacy test values. If we compare a time series produced for parameter equal 4 with time series generated by systems with different parameter of the logistic map. So we can see that if we compare our original time series with time series from shifted parameter value, then the value of conjugacy test, at least for small t, so for small pushing, so for small value of pushing the timing forward, then you can see that conjugacy test is changing continuously, like, at least from the experimental point of view. So the farther, the more the parameters of the system change, the higher value of conjugacy test. So it's like indicator of how similar behavior between those two time series is. If we choose the parameter t of the conjugacy as to be higher, so we iterate our time series much more, then we can see that that we very quickly get this very high, very steep shape of the plot. So the higher the t is, the more the chaotic behavior of logistic maps comes into effect, and we can modify, we can use different values of t to maybe to see how actually the values are sensitive to time. So the fact that we get eventually we get this sharp slope might be indicator that the time series for parameter 4 is not actually conjugated for smaller for this different parameter value. But this continuous change is what we like, because in real world data we don't expect to time series to come from exactly the same system. And the further example is comparing logistic map with 10 map. From theory, we know that those two systems are conjugated, and if we start very naively again with two time series, one comes from logistic map, another one from 10 map, we'll get, and we use again the identity as this conjugating map, then we get a high value. So this is a poor result for something that we theoretically know that should be conjugated. So for this example, we started to, it's still one-dimensional case, so it's manageable. So we thought, oh, okay, but maybe because, yeah. So if we use the identity map naively, then we get high value. But if we use as an H this the correct map, then conjugacy test gives us what we would expect, so the very small value. But this is of course cheating, because how do we supposed to know this H, right?
Yeah, we know, but we want the other example.
Yes, so this was the starting point for maybe actually finding it. So use the conjugacy map to find some kind of approximation of this H automatically. Of course, we know this is a super difficult problem of finding such a map. But we decided that maybe there is at least there might exist a heuristic for finding it. So what we did, we developed an algorithm that will try to approximate such a function. And how we did it. So instead of looking for exact formulas, we consider cubical approximations of map. So what cubical approximation of a homeomorphism for this one-dimensional case is just if I say this this map, which is just square of x, then cubical approximation of this map, this green map, is just this set of cubes. So in particular, we define the space H as a set of all cubical approximations of homeomorphism between the unit interval. So instead of considering analytical formulas, we started to look among all cubical approximations of homeomorphism for the best such approximation that will minimize the conjugacy test. And how can we find this best choice? Because this is still, we reduce the number of possible homomorphisms, but it is still a huge set, because for this particular case, when we have just a cube, just a set where we have, I think, 21 times 21 cubes, the number of all cubical homomorphisms is still huge, so there is no way of testing all of them. So we tried to create some kind of gradient descent algorithm, and this is very this is a pseudo code of the algorithm that we use. So it goes as follows. So we start with our initial guess for the connecting homomorphism between our 2-time series. And what we are doing, we fix a number of steps, and in each step we are finding a neighbor of our cubical homomorphism, where by neighbor of cubical homomorphism I mean another cubical homomorphism that differs just by a single cube. So among those cubical neighbors, I look for the one that will minimize conjugacy test score. And there is also a small technical thing here, is that I don't allow to flip a single cube if I change a single cube in my cubical homomorphism in some step, I don't allow to flip the same cube in the next case steps. This is a technical thing that allows us to escape local minimas. But the whole algorithm is also super easy. And using pictures, it looks like this. So if I very naively guessed, and also very wrongly guessed that conjugacy map, this connecting homomorphism between logistic and 10 map is x to the power 5, then what algorithm will do is, among all flips of cubes, so among all neighbors of this cubical homomorphism, we will find one relation of adding of a cube that will give me a better value of conjugacy test. And in each step, I'm changing a single cube that allows me to improve the conjugacy test score. And I'm doing it for example, for 1,000 of steps, and I see how the score is decreasing. Sometimes it increases because of this additional assumption that I cannot add or remove the same cube for k consecutive steps. But as we can see, this additional, this extra element of the algorithm increases locally the conjugacy test value, but it also means that allows us to escape those local minimas.
So k is like a fixed parameter?
Yes,
Or-
yes.
So you just take k, you guess k.
Yes, yes, yes. And we can see that for this experiment, we get a very small value for at about 600 after about 600 steps, and then we kind of reach the plateau. We can't get anything better. And so these are this was our starting point. So we had this naive first guess as x to the power of 5 is the homeomorphism. After 2000 steps, we will get a map like this. Okay, okay. And after 400 steps, we get things like this, and eventually at the step 612, we get this minimal value we obtained, and you can see that it's actually get us a quite nice approximation of the right homomorphism. Of the homomorphism that is theoretically the right connecting homomorphism between logistic and the Denmark. Yeah, so we were very happy about this result. This is of course a simple one-dimensional example. We are currently thinking if this could be generalized to higher dimensional problems, and if this could be optimized, because all of these are still like prototypes. We think that the algorithm can be also optimized. It's a naive construction of this gradient descent, but those experiments gave us hope that that we can optimize this choice of the age that is required for conjugacy. Okay, and also we did plenty of experiments in the paper. I will just mention a few of them. So Justyna mentioned that the classical use of FNN is for estimating the embedding dimension. We've shown that conjugacy test also can be used for this purpose. So what we have here is our plots where we compare using conjugacy test plus different embeddings of the Lorentz attractor. So for example, this is a comparison of embedding of Lorentz in one dimension and in 2 dimension. The second plot corresponds for a comparison of second dimension with third dimension and so on. And we can see that this is also a heuristics, but we can see that after comparing 4th and 5th dimension, the changes will really get smaller and smaller. So this might be indication that that when we change from 4th to 5th dimension, we don't get any new information. So maybe the 4th dimension in this case is enough.
3 versus 4, yes, does not. 3 versus 4 gives, let's say, relatively small values of conjugacy test for t, let's say, less than, I don't know, 25. So its sample also says that embedding in dimension 3 is, let's say, enough. I mean, passing to higher dimensions does not give you, let's say, much more information about the system. of course, here we see the divergence with t, yes, so if t is large, t is our parameter, because we still compare very, very long time series. I mean,
Yeah.
our time series, I don't know how many, 20,000 or
Something
like that,
series.
but t is a parameter. Like here, this is a chaotic system, so if you take t
Large enough,
large, then
that
it will divert a bit, but for some, say, reasonable values of t, this conjugacy test computed over very, very long time series, if it is embedded in correct dimension, gives you a low value. Yes, so it somehow, it also indicates that embedding in 3 or 4 dimensions.
And so this was another example of experiments that we did is it's again a toy example where we compare rotations or irrational rotations in a circle and on torus. So maybe I will just mention this. So we have a rotation on a circle by irrational value alpha, and the second time series is irrational rotation on a torus, where in one direction we rotate using the same value as on the circle, and we have some other value in the second dimension. So if we compare those two time series in different order, because also as Justyna mentioned, conjugacy test is not symmetrical, depends which we compare with, which time series we compare with which, then we can notice that if we compare the rotation on a circle with the torus, we can get a higher value than when we do it in the reverse order, which might also suggest that this time series on the torus contain more information. This is very simple, but if in particular the rotation in torus instances contains the rotation that is happening just on the circle. So this testing of including of containing another process can be also maybe indicated by conjugacy test.
In this comparisons, what key do we take? Just equal to what? Or?
T I think I usually took t equal to 5 or something like this. And I think in my last slide only I'm using it to also show you that here I was comparing two time series. They both were just rotations on a circle, but I wanted to see how our statistics are sensitive to noise. So you can see the message from this slide is that conjugacy test is in this at least case is also continuously depends on the level of noise. So in comparison to, for example, FNN, I mean KNN is also behave this way, so it's kind of continuously change with the noise. But for example, FNN is super sensitive to the noise, while conjugacy test and KNN is not. And this is also something that what we like about conjugacy test, because in the end, we are currently trying to apply this conjugacy test to some real world data where, of course, we expect to see a lot of noise. So this is a nice property. And I think I will stop here. There is this some implementation of this conjugacy test on the GitHub, and the paper is under review and also on the archive. So thank you.
So are there any questions? Please.
I have a question. I have a question regarding your search for the conjugacy, I will call it like that. So when you are looking for this H map,
Yeah.
and you want to approximate it by the cubes, because I didn't understand this part of. So do you fix the resolution? Do you fix the length of those squares? Or do you try to change, like increase resolution at every step?
That's also a plan for the future. For now, we just choose a resolution.
You fix the cubes and then you
Yes, among this fixed resolution, I'm looking for the best approximation.
But then you can apply this algorithm another time.
Yeah, but this will be extremely slow, obviously.
Yeah,
If you try to do this for every resolution, it's already.
Yeah. But that is one of the idea that maybe we can start with a small resolution, a small number of cubes, then and we run the algorithm, and after you find the low resolution approximation, then maybe you can make cubes smaller and
improve it.
So,
have better starting point.
Yeah, but
something like that. You don't start again with the same H0, but with something better.
Yeah. And we still are aware that this is slow for now, but we also are aware that this is in general, from the theoretical point of view, super difficult problem of finding something.
I mean, yes, recently we find a work that deals to artificial neural networks. So, because approximate age, but it's a sort of like a black box way of doing things. But it's so for us it's not that interesting. But in fact, it's the problem of approximating. Yes, and mapping.
Finding Michał. So we might be common about Michał. So finding, checking if these places are common. Classical problem, which is undecidable. So essentially, there's no algorithm to solve it. Even if you represent spaces with any type of representation. This problem is more difficult because not only we want the homeomorphism, but we also put some dynamics. So, I mean, we are looking at some partial things by definition. That's something we should be aware of. So we don't solve the problem functionally.
Yeah, but the fact that at least for so simple problems we can automatize it, and we get something that gives the right solution is something that gives hope that.
I think what was important in the last example is that the answer is kind of non-binary, that it may give us some notion of proximity and dynamics. We're trying to fit the best possible conjugacy map that we can find. It gives them kind of an upper bound of the language, which may be interesting both from practical and theoretical perspectives. Something I was trying to speak on. So we are trying to speak on it.
Yes, like maybe the future, yes, we would like to have a sort of framework like pipeline to test this conjugacy between time series, and maybe firstly one can apply some computationally less demanding test that if one of them will already give like negative answer, then you know that okay, that does not matter, does not make sense to apply this conjugacy test machinery further. But if you know there is already some chances, that the systems might be conjugate or semi-conjugate.
Okay, so you mean like a set a series of tests? You test it on one
Yeah,
level,
yeah.
then remove it if it doesn't fit, and you do this this quote unquote. Makes sense.
Please.
So a vendor you can result of this sort. So if you have two dynamical systems and the map H, if conjugacy test converges to 0, then you, under some condition, claim that H is true conjugacy. Is it
Yeah,
possible?
I mean, it's because it's like in the theorem is the opposite way.
Yeah.
Like, I mean, if it's semi-conjugate or conjugate, then conjugate is the 0. So it's so maybe, I don't know, maybe in the future we can turn it into some, let's say, statistical test, more like.
We don't have a counterexample.
Yeah.
The other application.
Yes.
You would say something like for all possible H, this goes to 0. No,
No, I mean for fixed
for
H.
one possible H.
If you want to
Okay,
check
then
if it's
this should be a
conjugation.
conjugacy, yeah.
Yeah. Yes. So somehow, if you want, just to test if two time series they represent conjugate trajectories by whatever age, then of course it's like you need to have find sort of candidate for age. Yes, but sometimes people are interested maybe in testing a particular age, maybe like one time series if it maps, for example, by some simple time delay, some time shift with the other one, and then like you do not test conjugacy and full generality, but then you check if systems are running in correspondence by this particular class of maps.
Justyna mentioned, so I mean, we don't have an estimate of the number of maps you learn between the 10 and the logistic, and we've already taken 20 groups that are approximated and every single one of them. And the number of the order of 10 to 14, which is a big number. So in practice, checking every single one of them is a futile. Good way of sampling from this place, perhaps, in terms of IP distance. But also we do not know. That's what Justyna mentions. Is a very people are trying to put neural networks everywhere. So we also put neural networks. This problem. They are finding a minimal local minimum of some function. Question how many local minimum you choose. It's not really deep, but based on attraction there exists in those problems, we do not know. And I would be surprised if there is unique local minimum.
Okay, I think we will now end. Actually, I have a question, but I think I will do it after because our time is up. So thank you very much.